His pants got ripped. Yeah, no, look at the sign. It was like 4. And he probably got glasses too.
I guess, but how much is
Really?
it?
I want it like
If it's a PDF.
I mean, I did a good job of reading. We should get up.
You didn't go to the...
I went down. I think it was in Mikey's late. Yeah, one that's like, his drink was very. It's like, should we come look at this?
Is it the mic that likes stand?
Wow. I just saw a lot of doubt. It's like space.
Okay, good morning everyone. Good morning. So we'll get started on radiation heat transfer. I'm going to very briefly go over what we did last class because we're going to use that to solve some problems today. Once we solve problems, these ideas will be a little more clear in our mind. Okay. So our primary aim in radiation heat transfer, remember from last class, Q double prime radiation is epsilon E suffix B alpha times G. This is the most simplistic scenario, okay? In this particular scenario, I'm not looking at the effect of the geometry of the surfaces which are interacting with each other. I'm not looking at the distance between the surfaces that are interacting with each other. I'm not looking at the total number of interactions of a given surface with its surroundings. It could be surrounded by multiple bodies. Okay? So this is the most simplest form of the radiation heat transfer equation. But even here, we have a few obstacles. We don't know how to calculate epsilon. We have not defined what is called as an ideal body. We need to know how to calculate this irradiation and this quantity of alpha, which is the absorptivity. So these are our initial small battles. So each and every term, how do we get these things? And then how do we put it all together? And the last step in radiation heat transfer is, okay, if I have multiple surfaces conversing with each other, how do I include their interactions? Okay, that's done by means of what is called as the view factor. Okay. So towards this, I defined the following term, the intensity of radiation emitted. We are looking at emissive characteristics. That is, we are looking at all things emission related for the time being. We will then turn this on its head and say, okay, I'm going to look at all things that are related to maybe irradiation, incidences, and so on. Okay? So here we define intensity of emitted radiation. Intensity is, and as you know, radiation is a quantity that depends on the wavelength. It also depends upon the direction. So there are the spectral dependencies and the directional dependencies that we need to isolate. And this quantity essentially takes care of that. It's called I lambda comma E. Subscript E denotes it's for the emissive characteristics. Function of wavelength, lambda. Function of the directions as prescribed by the azimuthal angle phi and the zenith angle theta. This is for a spherical interaction. And I'm going to write the formula, and we're going to deconstruct this piece by piece from last time. So this is given as dq divided by three things: d lambda, d omega, and then dA suffix n. And each and every term, so dq. is the rate of radiant heat transfer from an emitting area about a specific direction and over a fraction of the wavelength range. Okay? So dq, rate of radiant heat transfer. So this is going to be in units of watts. About a direction, that is a specific direction, okay, as some theta and phi, and over a fraction of the wavelength range d lambda. Now I'm going to draw a figure that will represent what we saw last class. I'm going to consider this area which I'm going to call as dA. So dA is our area of interest. So this is the area from which emissivity radiation is emitted. By dA, watch this. The radiation that is emitted by dA is going to come in all directions and over all the wavelengths. So dA is sitting there doing its business, emitting radiant energy in all directions and over all wavelengths. Out of that, this dq is the rate of radiant heat transfer for a specific direction of the radiant rays emitting from the surface dA, and for a specific fraction of the wavelength range. Okay, so these are specific things. And we said that radiation is going to be treated as a surface phenomenon for us. So we imagine a hemispherical bowl placed over this emitting area dA, and all the radiant energy is falling on that of some unspecified radius, not really of interest to us. Okay, so this is some hemispherical bowl. Radiant energy, and I'm shading a small portion because I'm interested in the radiant energy emitted by the area dA and passing through that small shaded portion on the hemispherical shell. And that is the direction that I'm interested in. So here is the angle theta, and I'm not going to draw the other angles and so on. We have the angle phi, if you like. This is the angle phi. So for a specific theta and phi combination, I have this small area, and radiant energy is passing through that area. Okay? How am I going to characterize the intensity of the radiation through that area? I'm doing it by using a solid angle. And to understand this, let us imagine ourselves to be the following. Okay? So another figure, same thing, but I imagine myself as this observer who is sitting on this hemispherical dome, just for fun, okay? And I'm looking down on this area, and I'm saying that let's ignore all the radiation falling on me from every other source. I'm just going to look at only the radiant energy coming from the area dA and falling on me. So imagine yourself sitting on that shaded portion there. The angle d omega is defined as the solid angle that is subtended by this ideal observer as seen from the emitting surface. Okay, so if I draw that out, so that is the solid angle d omega, and d omega is the angle subtended by the observer as seen by the emitter, under the caveat that this observer is receiving only radiant energy from this emitter. Okay? And we were able to derive this expression for d omega last time. So d omega ended up being sin theta d theta d phi, and an important point to note is the following. I'm going to draw two area normals. One is the area normal of the area dA itself, so this is n hat of dA, so this is the area normal to the surface dA. I'm going to draw another area normal. This is on the hemispherical dome. This is this observer who's sitting and observing these things, so this is n hat observer, and please notice that the solid angle is defined only when the area normal of the observer is coincident with the line of sight from the emitter to the observer. Okay, what's the line of sight? Line of sight is I'm sitting here and I'm straight away looking there. That's the direction of the line of sight. The direction of the line of sight is coincident with the area normal of that observer, and under these circumstances we will define the solid angle. So here area normal is coincident with line of sight. This is the area normal of the observer, okay? So that's the fraction d omega there. And then dAn, we looked at it last class, and the basic idea is the following. Imagine yourself as the same observer but different locations in the hemispherical dome. So I'm sitting here versus I'm sitting there, okay? This is the angle theta. The intensity of the radiant rays that I feel as an observer, if I'm sitting and looking straight down on the area dA, is going to be much more than the intensity of the radiant energy I will feel if I'm sitting here and looking at the area dA. And obviously if I'm sitting right here, as we said last class, I will not be seeing anything at all. That area dA will be represented as a point. So my intensity is now a function of the angle, and the functionality is cosine theta. Okay? It's maximum when I'm sitting and looking down on the emitting body, and it is a minimum when I'm sitting at an angle of 90 degrees and looking at the emitting body. So we define this dAn, and let me write that out here. So dAn is the fraction of the emitted area, emitting area, about the direction theta and phi. These are all with respect to the emitting area characteristics. So dAn is nothing but dA times cosine theta. And if you perform all these substitutions, we get the following expressions for dq. And I want to make sure everybody is following me. This is the definition of the intensity of emitted radiation, and this depends upon the factor dq. In most situations, dq is what we want, and I lambda comma e is what we will obtain experimentally. And we have to go through with this definition because of the nature of the radiant energy being emitted by the surface. Okay? Now cross multiply. Stuff from last class, so we will solidify this in a minute. So dq is I lambda comma e lambda theta phi. D lambda, leave it like that. Then I'm going to have d omega times dAn. dAn contains cosine theta. So this is sine theta, cosine theta, d theta, d phi. Watch this, I'm going to divide through by the area dA. And this becomes the flux. Okay, so this is now dq double prime. But this is just the flux at about a specific direction, and for a fraction of the wavelength. What if I wanted for entire range of wavelengths and for all the directions? I integrate and I just get the emissive flux, the total emissive flux. Okay, so this is over all the directions around the hemispherical dome, and for all ranges of the wavelength, I get capital E is nothing but integral lambda from 0 to infinity, phi from 0 to 2 pi, theta from 0 to pi by 2, dq double prime, d lambda, and all of these other things, d theta, d phi. Okay, where I have divided by d theta and d phi for the dq prime, double prime. And if I write out the total emissive flux, then E is 0 to infinity, 2 pi, pi by 2. This will not have these terms. Just integral of dq double prime, that's correct. And the rest of it, I lambda theta phi sine theta cos theta d theta d phi d lambda. This is the net emissive flux. Okay, this is over all the wavelengths and over all the directions. Obviously, we will constrain ourselves to not integrate from 0 to infinity because I'm not interested in an infinite range of wavelength values. Okay, so that's what we'll be doing in the next problem. Alright. So let's do two problems today. First problem. There is a shiny surface, and we'll see what the notion of a shiny surface means in a few lectures' time. It's a shiny surface and it's emitting a radiant energy, and you're told that this intensity of radiant energy emitted is for certain portions of the wavelength independent of directions, and for certain other portions of the wavelength it's having a directional dependency. Okay, so shiny surface. For a portion of the wavelength from 5 micrometers to 10 micrometers, I lambda comma E, which is the intensity of the radiant energy emitted, is equal to the intensity which is independent of theta. This is for a wavelength range from 5 to 10 micrometers. 5, 10, and lambda is in micrometers. So this is 1, and then over the rest of the wavelength range, it's a function of angle as well. And you're given these functionalities in the form of a following figure. So this I bar lambda is called the spectral distribution. When something is specified only with respect to wavelength, it's called a spectral quantity. When something is specified with respect to direction only, it's a directional quantity. Most times in radiation, it's a spectral and directional quantity. Okay? So here, I lambda bar as a function of lambda is given as follows. Can somebody tell me the units for I lambda comma E? We have this ratio there. What's the numerator? What? What's the first term in the denominator? d lambda is wavelength. Its unit will be in micrometers. d omega is going to be in we live in a three-dimensional world, most of us. What's the unit for a solid angle? Steradians. It's going to be steradians, and then dA is meter square. Okay, so the unit for I lambda comma E is this very weird quantity, watts per meter square, micrometer, steradian. Okay, it's a mouthful. So that's what you're plotting here, and I'm giving it as the following. Okay, so 0.1, 10 and 40, so lambda in micrometers, and I lambda bar in watts per meter square, micrometer, steradian. The first value is 10 to the power 4, the second value is 2 times 10 to the power 4, so this is 10 to the power 4. 2 times 10 to the power 4. So between a wavelength of 0.1 to 10 micrometers, the value of I lambda bar is 10 to the power 4 watts per meter square, micrometers, steradians. And then from 10 micrometers to 40, it's going to be double that. Okay, the functionality is given as the following. So 0, pi by 2, pi. This is the zenith angle theta. It's independent of the angle phi. So just a function of theta, f of theta. This is 1. Can somebody tell me what this function is? It's 0 at 0, it's 1 at pi by 2, and it's 0 at pi. It has to be sine theta. Yeah? So f of theta is just sine theta. What you are asked to do is the following. Obtain the emissive flux, the total emissive flux, which is this capital E for a wavelength range from 5 micrometers to 40 micrometers. Okay? So obtain the emissive flux, which is capital E. Emissive flux is going to be in units of watts per meter square. Okay, that's just a radiant rate per unit area for this particular wavelength range. Using the plot given and using the fact that this is at some time independent of the angle and at certain other times dependent on the angle, and we're going to call this by a specific name. If the intensity of radiant energy is independent of angle, then such an emitter is called as a diffuse emitter. And I'm going to define this in the next problem. Okay, so this is just the start of our pain. All right. How to solve this problem is a direct application of the formula, keeping in mind that I already know what my limits of integration are. Okay? For a portion, I have to first of all break it down into two pieces, and there is a caveat in this particular problem. I want to obtain the emissive flux for a particular direction where theta ranges, where theta is 45 degrees, or an entire range of theta. Let's say over an entire range of theta. Why restrict ourselves? So just obtain the emissive flux. Okay, that's all they're asking you to do. It's a direct application of this integral. All you have to do is split the integral into two parts. There is a part where the intensity is independent of the angle. That integration is going to have a fairly straightforward, smooth thing. It's just going to be integral with sine and cosine theta. There is a part where the intensity is a function of theta. So not only do I have the sine and the cosine and the capital E expression, I will add in an extra f of theta. Okay, so I'll write it down. So E, by definition, what we have there is 0 to infinity, 0 to 2 pi, 0 to pi by 2, I of lambda, comma E, sin theta, cos theta, d theta, d phi, d lambda. And this I'm going to break into two pieces. Why am I breaking it into two pieces? Is because I see that if my wavelength range is from 5 to 40 micrometers, then from 5 micrometers to 10 micrometers, you see that it is independent of theta. So I just plug in the value directly there. And then from 10 meters to 40, I have to include the theta dependence. So this is from 5 to 10. I of lambda comma E is just I lambda bar. This is just a function of lambda, so I lose the theta and the phi dependency. D lambda, because all the other quantities are independent of the wavelength, and then this is 0 to 2 pi, 0 to pi by 2, sin theta, cos theta, d theta, d phi, plus the second portion kicks in. From 10 to 40, I have the angle dependency, so this is now going to be 10 to 40. You see, I'm not interested in 0 to infinity because it is 0 after 40 micrometers, it is 0 before 0.1 micrometers, so who cares? Integral from 0 to 2 pi, 0 to pi by 2, I lambda comma theta. So that's going to be I bar of lambda times f of theta, sin theta, cos theta, d theta, d phi, d lambda. Does this make sense to everybody? This is just an application of the formula. There is nothing to think here. The thinking has already been done for you by saying that this is a combination of these two functions. One is independent of the angle over a portion, the other is dependent on the angle. I just want to do one of these integrations because that is something that we'll keep seeing again and again. So look at this term. Okay, I'm going to call it as Roman numeral 1, Roman numeral 2, I'm going to do the integration for 1 just once. Okay? Integral of I lambda bar. That's fairly straightforward because that is just 10 to the power 4 over 5 micrometers to 10 micrometers. So this is 5, 10, 1 times 10 to the power 4 is the value of I lambda bar right from the plot that is given to me, over the wavelength range d lambda, and integral 0 to 2 pi, 0 to pi by 2. Sin theta cos theta can be written in terms of the double sine angle. Sin 2 theta is 2 sin theta cos theta. So sin theta cos theta is sin 2 theta by 2. So this is 1 by 2 sin 2 theta d theta d phi. Okay? This is trivial. It's a constant multiplied by 10 minus 5. So this is 10 to the power 4 times 10 minus 5, so many micrometers. Okay? There is only a theta dependency, there is no dependency on phi, so I do the integral over d phi first, and that's going to just give me 0, 2 pi minus 0. And then half integral 0 to pi by 2 sin 2 theta d theta. Okay? And so, moral of the story, this entire thing is 0 to 2 pi d theta d phi. If you do the integral, sine 2 theta is going to give you minus cosine 2 theta, and a factor of 2 once again because it's sine 2 theta, and substitute the limits, you'll end up getting the following. This one gives you 4, 10 minus phi, 2 pi, 1 by 2, minus 1 by 2 times cosine 2 theta from 0 to pi by 2. That's the integral of sine 2 theta. That's cosine of 2 times pi by 2, which is cosine of pi, which is minus 1. Cosine of 0 is 1. Minus and minus becomes a plus. So this is eventually minus 1 by 2 times minus 1 minus 1. And so, factor of 2 and 2 cancels off. Minus, minus and minus becomes a plus. 1 plus 1 is mostly 2. 2 divided by 2 is 1. So all of this gives me just pi. Okay, so this entire setup here gives me pi. And so what I want to say is the integral from 0 to 2 pi, 0 to pi by 2, sine theta, cos theta, d theta, d phi is just equal to pi. What are the units? We're all awake? Steradians, there's nothing to think here, which is the problem mostly. Okay? So pi steradians. Alright, 10 minus 5 is 5 micrometers. And I now look at all the units that I end up getting. Do you guys have a question there? Question?
They were talking about the pronunciation of the steradian.
Is it what? Solar?
Sorry, star radians or sun radians?
Steradians. S-T-E. Radians with the Steve. Okay. So if I look at the net units that I end up getting here, it has to work out to give me emissive flux. So 10 to the power 4 has units of watts per meter square micrometers steradian. So this guy, meter square, micrometers, steradians. 10 minus 5 is 5 micrometers. So this is micrometers from there. And then that big thing there is just steradians. And so I end up getting emissive flux. Okay, so my units work out. Everything works out. So that entire thing is watts per meter square. And likewise you have to do the integration for f of theta times sine theta times cosine theta. I'm going to leave that as an exercise. I will post the solution, but it will end up being sine square theta because f of theta is sine theta. Sine square theta times cosine theta. You'll have to use the sine square answer as 1 minus cosine square, and then you'll have to use the cosine 3 theta formula. Lots of manipulation, or you can just call it a day, plug it into Wolfram. Okay? So, if that was your next question, I have answered it. Alright, so eventually the answer ends up being the following. It's approximately 4.5 times 10 to the power 5 watts per meter square. So E. This is after evaluating both the integrals 1 and 2. Okay? So that's what E ends up being. Okay, so I want to go to the next problem, slightly better than this. I'll pull the board up later on. Next problem, we have a set of areas as following. And once again, we are not doing anything related to calculating the radiant heat rate and so on. This is just understanding the formulae that have been presented, using them a couple of times. Okay, just getting juiced up. I have a square plate of a certain area. So let's call this as area A1. It is 10 to the power minus 4 meters square, so it's a really tiny surface. This is emitting radiant energy diffusely. So A1 what's the meaning of a diffuse emitter? A diffuse emitter is any surface that emits radiant energy without any angle dependence. It is going to be the same in all directions, or it's going to be completely independent of the angle. Okay, so there are two types of diffuse emitters. There's an ideal diffuse emitter, which means that it emits radiation evenly in all directions. All directions. And I'm going to draw a figure that will help us understand this. So if I have an ideal emitter, so those two small lines represent the extent of the ideal emitter, and if I look at the emitting rays, they are the same in all directions, the intensity. So the intensity is the same in all directions, so the intensity is independent of the angle. Okay? Independent of theta and phi. That's an ideal emitter. It's typically called as a black body in your book. And I said that we will not be using that terminology here. The second one is called as a real emitter, a real diffuse emitter. Even here, there is no directional dependence on the intensity emitted, but the intensity emitted is not the same in all directions, it is completely random. So there is no discernible functional dependence that you can glean from the intensity plot. Okay, so here, for a real diffuse emitter, so there is no discernible angle dependence that you can see, and it is completely random. So even here, intensity is independent of theta and phi. It is just that the ideal emitter is much more easily amenable to mathematical relations because it is the same in all directions. And so using the characteristics of an ideal emitter, which will be given by Planck's theory of radiation, we will use that as a benchmark against which all real surfaces will be compared. Okay? And that's where we are heading towards in the next lecture. So you are told in this problem that A1 is an ideal emitter, ideal diffuse emitter. I'm going to place this hemispherical bowl over this guy. And here is the area A1, of course. In the first instance of this problem, there is an observer who is sitting 50 centimeters away from this area on this hemispherical ball. Okay, so the radius of this hemispherical ball is 50 centimeters. And there is an observer who is sitting and aligned with the hemispherical ball in the following manner. So this is another area A2. This is the ideal observer, as I mentioned at the beginning. And the angle between the radiating surface, emitting surface and the observer is 60 degrees. And this observer does not receive radiation from any other surface besides A1. Only from A1. Okay, so this is the problem setup. You are asked to do the following. If the emissive flux coming out from the surface A1 is 5 times 10 to the power 4 watts per meter square, so I write it down somewhere here. So E1 is 5 times this is given to us, so this is the emissive flux coming out from that surface. Somehow the measurement was made and they're giving you the value. They're telling you, okay, hey, if this guy is an ideal diffuse emitter, obtain the total intensity of the radiant energy emitter from A1. Obtain the total intensity of radiation emitted by A1 about any direction. And it's purposely said it's about any direction because there is no directional dependence for this body A1. So it has to be the same in all directions if you're calculating the total intensity. And the total intensity is defined as the following. This IE is integral lambda is equal to 0 to infinity I lambda comma E as a function of lambda d lambda. So let's do this first. We are given the emissive flux. We are asked to calculate the intensity of radiation. There is a relationship between emissive flux and intensity of radiation. We have that integration done somewhere. So I'm just going to recall those results. Okay, so recall for this surface A1, E1 is the emissive flux. It's integral 0 to infinity, 0 to 2 pi. 0 to pi by 2 because it's a hemisphere that we are considering as the boundary for all these radiant energy to be hitting upon. I lambda comma E lambda theta phi sin theta cos theta d theta d phi d lambda. Okay, this is the main expression. In this particular problem, for the surface A1, you are told that the intensity of radiation is independent of direction. They're not telling you to directly, they're telling you that it's a diffuse emitter. It's an ideal diffuse emitter, so the intensity is the same in all directions. So actually I lambda comma E is not a function of theta and phi. So I can rewrite it in the following manner. This is 0 to infinity. I lambda comma E of lambda only, no theta and phi. D lambda 0 to 2 pi 0 to pi by 2 sin theta cos theta d theta d phi, and this is because A1 is an ideal diffuse Does this make sense to everybody? Yes, this question.
On the board you
Oh,
wrote there,
I just erased it.
it said the real diffuse emitter is also independent of,
It's also independent, right?
is that the same then?
No, it's not the same because here this intensity for an ideal emitter is equal in all directions. But that's not the case for a real surface. It is just that it is random in all directions. So that randomness initiates the fact that there cannot be any dependence on the angle theta and phi. Okay? So it's almost like thinking about anisotropy versus isotropy. Anisotropy means that there is a directional preference. So if something is anisotropic, or what you call in optics as a specular surface, there is a certain directional dependence of that surface. Okay, here that is not the case. There's only a spectral dependence. Alright. And so this quantity, I lambda comma e integral from 0 to infinity, is the creature that we are looking for. So this is your IE. And if you recall, just a few minutes back, some of us may remember this was equal to pi steradians. So we are already done with the work. I have E1, which is 5 times 10 to the power 4 watts per meter square. This is equal to IE, so that big guy is IE here. The total intensity of radiation emitted by the surface. This is the same in all directions because it is an ideal diffuse emitter. IE times pi steradians. So what's the unit for IE? It's going to be 5 times 10 to the power 4 watts per meter square steradian. Notice that you are losing the dependence on the micrometer because you are integrating over all the micrometer values. You are integrating over the wavelength. If I looked at the spectral directional intensity, which is this creature I lambda comma e, so this is the total intensity. And to distinguish this from I lambda comma e, which is having units of watts, meter square, micrometer, steradian, this is called as the spectral directional intensity. And sometimes to make sure that this is different from that, we use the word spectral to denote the wavelength dependence. But in many situations, this could just be a purely spectral quantity without any directional dependence, which is what we have as a case of an ideal diffuse emitter. Yes, question?
Where did the pi go in the top equation? Did it not account?
Yeah, I swallowed it lunchtime. Okay. Thank you. Next part of the question. Last part. What is the heat flux that is received by the area A2? What is the flux received by A2 under the caveat that the size of A2 is much, much smaller than the distance between the two areas, which you can see 50 centimeters versus 10 to the power minus 4 meter square. So small size. And this is also under the further additional caveat that A2 receives energy only from A1. Okay, so whatever is sent by A1 in the direction of A2 is all that A2 receives. So let us start off with the fractional form of the rate of radiant heat transfer, so dq. I'm going to give it a subscript from 1 to 2 because it is energy coming from 1 going to the area 2. Okay, so dq 1, 2. This is the rate of radiant heat transfer over a particular wavelength range and for a specific direction. So this is going to be I lambda comma e lambda theta phi. This is the radiant